Okay, I'm really excited to talk about Gibbs Free Energy today. So we need to review the second law of thermodynamics first, because that has to do with entropy, which, remember, is the measure of disorder or how dispersed energy is in a system. And the second law of thermodynamics says that a reaction is going to be spontaneous if the change in the entropy, right, which we know is a big capital S here, is greater than the heat, that's Q, divided by the absolute temperature, which would be in Kelvin, of course. And that would be given that that temperature is staying the same, right? We have a constant temperature, constant pressure. If delta S is positive, then that means that the reaction is going to be spontaneous. And that makes sense, kind of, it jives with what we know about entropy, because we know that systems like to move towards disorder. That's the lowest energy kind of configuration, is to have energy more dispersed throughout the system. So delta S being positive is a good thing because it's measuring a greater disorder at the end in the product side compared to the reactants. Now, this is really the second law from a chemist's standpoint, I would say. Physicists, of course, would state it in different ways, and it really just depends on kind of the systems you're looking at. But if we're thinking about chemical reactions, this is a good way to go. And this is where we get into Gibbs Free Energy, which I think is kind of fun. Because it really is just a working and reworking of this law, but we just need to play around with it a little bit. So let's remind ourselves that the heat, if we're thinking about chemical reactions, is equal to our delta H, which is our heat of reaction, or enthalpy. So the change in the heat of the reaction is the heat, right? So we could rewrite this as delta S is greater than delta H over T. And if this condition is true, if delta S is greater than the heat of our reaction over the temperature, then that means that the reaction will be spontaneous, right? So that just has to be larger than this quantity here. If we rearrange to get all of these variables on the same side, then I could say, well, 0 over T minus delta S. Get careful with my deltas, they get a little bit out of control. All right, so now if I do some rearrangement here and set this up, then we can say, well, if this condition is true, then a reaction will be spontaneous, right? So if this, then spontaneous. If this, then spontaneous. Now, if we multiply everything by T through here, then we get that, you know, and we'd have to kind of do some rearrangement, that delta H minus T delta S, if that is less than 0, then it's spontaneous. And again, we have to keep that kind of constant temperature and pressure in mind throughout. So kind of doing some rearrangement here, then we end up with this value. If this quantity is negative, then, so if this whole quantity is negative, if negative, which is what this is stating, right? If it's less than 0, then we have it spontaneous. So that means that if that whole quantity is positive, so if we calculate this out, we have our delta H for the reaction. We know our delta S for the reaction because we can look that up in thermodynamic tables. If we know the temperature at which it's occurring, if it's positive, then the reaction is non-spontaneous. Which doesn't mean that it can't happen. It just means that we're going to have to do something to it. We're going to have to put energy into the system in order to make it go. And then if it's equal to 0, so right now we just have a less than here, you know, and if greater than, if positive, then it's non-spontaneous. If it's equal to 0, then we're at equilibrium. So this is one way that we can use that is at what conditions would I be at equilibrium? At what temperature would I be at equilibrium? Or how would I have to change things in order to get to this quantity equal to 0? Okay, and again, at constant temperature, constant pressure. Okay, so I haven't talked about Gibbs yet, but we're getting there. Okay, so when delta H minus T delta S is equal to 0, we say the reaction is at equilibrium. And if that whole quantity has any other value, then the calculation gives you Gibbs free energy. So whatever it is, whether it's positive or negative, that is going to be your delta G, which is very exciting. I love talking about Gibbs free energy. It's kind of a weird quantity. And actually, this shouldn't have a this shouldn't have an apostrophe here because it's actually Gibbs. It comes from Josiah Willard Gibbs. So it should be Gibbs's Free Energy. So, you know, not an English major. Okay, so the symbol that we use to identify Gibbs Free Energy is a capital G, which makes sense for once, unlike entropy, which I still don't understand. So Gibbs is a really important American chemist. We have a few of them. You know, he was around in the 1800s and into the early 1900s, and he was well respected in his field. He has a number of different models for looking at thermodynamics and physical chemistry, and also, you know, so because there's physical chemistry, it's a sort of borders the physics realm. So he's very common in physics type problems as well, and mathematical models. I mean, there's that nice overlap of all of those different disciplines, and Gibbs was really right at the center of it. Albert Einstein actually was one of his fans. He said that he was actually the greatest mind in American history. So that's an Einstein quote, greatest mind in American history. That's Gibbs, kind of an important dude. And this is kind of an important equation. I always tell my students that, you know, if you're going to remember one, or if you're going to get one tattooed on your body, then it should be the Gibbs Free Energy equation, because it's that important. So if delta G is negative, then, right, if we say that this whole quantity is less than 0, if delta G is negative, then we say that the reaction is spontaneous. And I'm going to put a little plug in just to remind you that, and if you've seen any of my videos about entropy or spontaneous reactions, spontaneous does not mean instantaneous. That doesn't mean that the reaction is just going to occur just like that, but it could be over long spans of time. It's just that you don't have to put the energy in order for that reaction to occur. And if it's positive, the change in Gibbs free energy, then it's non-spontaneous. So Gibbs free energy is so very important because it's going to give us information about how chemical reactions can occur and what we'd have to do, how we'd have to tweak them in order to get them. And it really combines together a lot of the thermodynamic concepts that we've seen throughout. So we're looking at enthalpy, and we're looking at entropy. The temperature is important, and that kind of all comes together for Gibbs free energy. Now we could also talk about it at standard conditions. So if we put our degree symbols on everything here, all of my state functions here, then that would be, of course, at standard thermodynamic conditions. Which is somewhat implied in all of this because we have to be at constant temperature and pressure. Otherwise, we have too many variables changing for this to be true. Now, the units on G, if we're thinking about SI units, it would be, you know, joules per mole, but the standard unit for G is the kilojoule per mole. So it's in the same unit as enthalpy. Recall that our entropy is usually in joules per Kelvin, so our temperature has to be in Kelvin, and our joules per Kelvin would have to be converted in order to get to the kilojoules per mole. So that's an important thing when you're doing problems around Gibbs free energy. Make sure that you have the right units for your energies. It doesn't really matter which way you go, although you're going to be reporting them in kilojoules. So it's always just easier to put your entropy in kilojoules. Why they don't just report it in kilojoules, I don't know. I'm not sure. No one consulted me. Okay, so let's think about this kind of conceptually then. So if we're thinking about our delta G equals delta H minus T delta S, which is going to be the most important equation for the next few weeks of your life because you won't be able to get it out of your head, then let's think about the different signs and the implications then. So let's talk about our enthalpy. Let's talk about our delta S, and then kind of the impact that would have on delta G, because mathematically speaking, there's only certain things that are going to be allowed that are going to give positive and negative values for Gibbs free energy. So we know for enthalpy that a spontaneous process is going to be an exothermic one. So let's think exothermic. What is the sign on delta H going to be? It's going to be negative, right? So it's an exothermic reaction. And what do we know about entropy? We know that entropy is a good thing. Systems like to have more entropy, more disorder. It's a positive thing. So if I have more disordered system and an exothermic reaction, if we think mathematically about this equation, I'd have a negative value here, and my temperature is in Kelvin, so that's always going to be a positive number. And if my delta S is positive, I'd have a negative minus a positive, right? So I'm just going to get more negative. Then that's going to always give me a negative delta G, right? And if I always have a negative delta G, then that's always going to be a spontaneous process. We'll go spont. Always spont. Okay? Always spontaneous all the time. Now let's do the opposite. Now if we have an endothermic process, right, where my delta H is positive, and I have a system that is getting more ordered, right, so I'm going from maybe a phase where I have a bunch of gases and then I'm putting them all together and I'm forcing them into either liquid or solid phases, or combining them together and making them less free to move around, then that would be a negative delta S. So if we think about this in terms of mathematics, right, just from a mathematical standpoint, if I have a positive delta H and then a negative delta S, that's going to be a positive. The negatives will turn into a positive. Two negatives make a positive. That means this whole quantity is always going to be positive. So my delta G is positive, which means that it's never spontaneous. So anytime I have an endothermic reaction that is getting more ordered, I'm never going to be able to make that happen without putting energy into the system. Now, the other kind of variations on these, where they delta H and the delta S have the same sign, are going to give you something kind of interesting to think about. So let's think about if they're both negative. If I have an exothermic reaction, but it's getting more ordered, right? Because that's what that means in terms of our signage here. Then what could that mean? That'd be a negative value here minus a negative value here. So that could get me to a positive value. That means it could be positive or negative. It could be one or the other. And the thing that's going to make all the difference here is the temperature. So this one is temperature dependent. So think about it. Which one, higher or lower temperatures, would give you a negative value? Well, if I have a very small number here, even though this is a negative, I'd have a negative value here plus a smallish number. I could still keep it negative. So I need to have a low temperature here in order to have a negative delta G. So this would be kind of spontaneous, spont, at low temps. All right, now let's think about our positive. So if we have an endothermic reaction and we're getting more disordered, so I put energy, more energy in the system than I get out, and I'm going to a more disordered state, then again, it can be positive or negative. Mathematically speaking, if this is a positive quantity and this is a positive quantity, then if this quantity is larger, right, the whole thing times my T is larger than whatever this is, then it's going to give me a negative value, and so that's a good thing. Or if it's smaller, then it's going to give me a positive value. So I can go either way. This is also temperature dependent. But this one's going to be spontaneous then at higher temperatures, because we want this value to be larger, because we want to subtract a larger number here from my delta H. Okay, so delta G equals delta H minus T delta S, and Gibbs free energy. It's going to be really important for predicting the spontaneity of processes. And now we can kind of start to see, well, how are each of these going to impact the overall free energy that is required, or that is available in a system in order for it to move around to do some chemistry. That's kind of what we're getting at with the free energy concept. So if you have any questions, as always, don't hesitate to reach out. Otherwise, I'll talk to you again soon.